This is a bit of a back to basics. I'll warn you a little bit about this. This is a lot of stuff that you think you probably learned a long time ago that you forgot, and a lot of it's kind of bled away and you don't really care about it anymore. But it might give you just a little bit of perspective on things. And that's really what a paradigm is. It's a perspective of how you look at data, how you access it, how you manipulate it. So, one apology first. I gave this talk somewhere else first. It was a nice dark theater. I did not have time to change the edit to do it a black on white. So I hope it comes through fine for everybody. That's me, so, from the Seattle area. Classically trained in hardware and software, which is very helpful for me. I tend to have done a lot of embedded. And even when dealing on big boxes, I still know how the transistors flip inside, so I know how to use it and how to understand it. Specialized in modern C++, I've done a lot of different languages. I don't want to do any of those other languages. This is my specialty that I like. Working on very complex problem spaces, but problems should not be complex. They should be simple to solve, reduce them down. If it's an easy solution, it's probably right. If you have a complex solution, it's probably not. Big stuff, little stuff. Recently started working with ISO. Work a lot with the evolution working group. That's the group that decides what features are gonna go into the language part of the compilers and stuff, not the library part. So, I have no interest in C#, Java, .NET, other BS. Perfectly nice languages. They have their place. It's not with me. It's just who I am. Okay, paradigm. Everybody's heard that C++ is a multi-paradigm language. And there was an original book definition that said it's imperative, procedural, functional, declarative, and object-oriented. And what does that really mean? We'll talk about each of those different styles. They're basically a paradigm, or these are the building blocks of how we build our programs, methodologies that we use for how we lay out our programs, and they have evolved over time. Some people think of, when they're thinking of paradigm, they're thinking bigger, more conceptual, big things of this is how the entire world works and this is how we do stuff. This is my, like a foundation library. Those have paradigms. They're a little different than these paradigms, and we'll get into some of those. Yeah, I was just saying there are others. But a paradigm, way of looking or thinking about something. If you work in an office as doing some administrative type tasks, you have procedures about the way you do things and process things. You get the form from the customer, you enter it, you process it, you stamp it, and you pass it on. That's the paradigm of how that works. Not to say that method is the only way to do it, but that's how your office works. And from time to time, you get a memo that says, we don't need to stamp it in 2 different colors. We only need the one color now. So we evolve our thinking also. It's one way of laying out and showing your intent of how you want other people to read your code, and it helps them understand what the layout and design is going to be, what you're doing, where you're going, how they should understand it. It's like the ideas of design patterns, whereas if you know someone else's design patterns or their coding style, you know what to expect. If you're using certain paradigms, it's easy to understand where people are going or what they're going to do next. So we have imperative, procedural, functional, declarative, and object-oriented. Imperative is a sequence of instructions, like if you were to leave a note for your kid, get up, brush your teeth, get dressed, go to school, come home, clean your room, do your homework. That's a directed list of what to do. And that's the way we all started programming. Mainline program, step 1, step 2, step 3. No little subroutines off of doing any of that. Procedural is still kind of the same way, but you took some common tasks out of that. And for first example of talking to your kid, clean up your room. That involves making your bed, pick up all your dirty clothes. Those are multiple steps that we bundled and put into a separate function, a subroutine. Functional is more of a data-oriented. A lot of other languages, like Haskell, use this, and it's very mathematical, procedural. They copy the data. Most data is const, so when you go to manipulate it, you get a new set of that data. You do steps to that. C++ cheats a little bit and doesn't do as much of that. Declarative is a lot more in the procedural, very broken down into functions that, rather than actually saying, do this with the data, it describes what it is, verb. And we'll get through examples of each of these. Object-oriented, most of all, you know object-oriented. You have a class, you have your data and your functionality, and they're cohesively bound together. And when it's a multi-paradigm, it's not really that you cross certain thresholds and now you're using a different paradigm. It's continual. Sometimes you're imperative, sometimes you're all the way to the declarative side. These are also, C is a multi-paradigm language. It can do all these. Okay, imperative, sequence of statements, step by step, very old school, your computer science 101 class. Very simple instructions. Oh, actually, there was more bolts there. Low functional cohesion, meaning everybody knows about all the data. Some of it's stored out in global space, some of it's local to your functions or in main. Really sloppy programming style. There are times when it's handy, but that's more of what you kindergarten. So we got I'm going backwards. Okay, in an imperative program, you declare a variable, you read it in, you do math locally. This is converting between Celsius and Fahrenheit, and you just print out the answer. That's the whole thing right there. You're told what the steps to do, all your data is local, and it's all exposed. Procedural is step by step, but you're breaking some tasks out. It's a derivative of imperative programming. They kind of build up from one to the next. So they're not really different, but they're a little bit better. Slightly more generic or imperative functions. So you actually took some of this stuff and broke it out. We'll see an example in a second. Slightly better functional cohesion. You hide data inside functions, or you do your math inside functions so your main line doesn't see what it was. So where we did the Fahrenheit conversion before, that's now in a function. That's all bundled away. If we wanted to convert the other way, we would have another function that was Fahrenheit to Celsius, and you would call that separately. And it was all hidden in there. You could switch the function of which one you were calling. Or the very first time I wrote this out, I actually did the wrong ratio in there. So it was much easier to fix. I did it in one spot. I think I entered 8/5 instead of 9/5 for degree. And I forgot to add the 32. Debugging. It can also be where you have all your data in the main, but you pass it. So you pass a vector, print it out, you sort it, you print it out again, and then we sum all of the even numbers, which is a function that's hidden in there. So we go through and just sum up all the even numbers, and then we spit that out. So main line, relatively more generic, broken out into modular pieces. Functional, I talked about, is much more mathematically typically based, like a Haskell. Typically, like Haskell is, all your data is const. It's immutable. You can't change it. So if you wanted to go through and sort a list, you would read it in and spit it out to a new list, or if you wanted to modify all that data. C++, we cheat, we like doing things in place. We don't have to go off and do extra allocations. Yeah, if you're pure functional programming, immutable, C++, not as much. So here's a simple example. We have a list of values. Here we don't actually go through and manipulate every single entry in there to add this up. We could very easily have iterated through the values and created an accumulator of them. But we have a standard library that just says begin, end on these. And we have a lambda. We just go through and add it up to the accumulator, and we return what the cumulative value is, and we spit it out. Here's another example, multi-step of, we have our list, we print them out, we do an accumulate, we do the sum, we know the size of the vector of doubles, and so we easily calculate the average. And we go through and do a transform, where we modify, we cheat and do the data in place and square them all and print them out squared. And then we calculate then the sum of squares. So one more square root on that, we would have had a standard, or almost a standard deviation. But that was just showing of using the data. The declarative, where we break things down more into functional pieces, we want to ignore really what the data is and say what we're doing to the data. Verb-centric, do this, do that. Data agnostic, hierarchical, so we have load, sort, reverse, transform, print. We were saying do these things, we didn't say what is the data and how we're doing it. So had we had different data types, we would still use those same verbs, but we would have different parameters, overloading. So here, let's go back and look at that. Main line, you don't know anything about the data. We even have an auto there. We just say, load it, sort it, print it. The functions themselves do it. So the load, I just stuff the data into a vector, return that. We sort it in place, and then we print it. You could be, instead of song titles, it could have been, states and capitals or anything you wanted to put in there. Another example of, this one is using a pseudo mixed paradigm. It's a declarative, but it's more of in a functional style. So we have our data, we copy if, and the lambda makes that decision for us. We transform it, we iterate through the data, and then we happen to square it in this case. Then I reverse it. We just use a library function that does that, same as if we had written a function to go through and reverse it. The library is good at this stuff, it has these things, let it do what it's good at. And then we just spit out each of them. Here again, the continuum. These were the base types, not counting object-oriented. So C++ adds some other language features on that. We have the object-oriented, and then templates, and the full standard template library. Object-oriented, you all know, your data and function members of the class cohesively coupled together and protected, encapsulation. It only exposes the interface that you know about, or that you want other people to know about your data, so you can change your implementation if you want without the outside world knowing. Low coupling. Classes can inherit functionality from other classes and inherit data. Nothing new. By the way, soapbox, a lot of people will tell you inheritance is bad. It's not all bad. There is good functionality to be had from using inheritance and dynamic polymorphism using a virtual mechanism. No one's throwing any stones yet, but I like static morphism, or also, but dynamic polymorphism has its place. So, okay, off the soapbox. more. It really helps you organize your data around how your code is clustered, and you can isolate it from each other. You can overload operators. So if you want to add something, you can decide you want to scale a matrix, or you can multiply two matrices together. That's a dangerous button to have. Okay. Classes should not know what other classes are doing or how they're implemented. They should only use the interface. Used to be friend was a really, really nasty word. It still is if you want to get into someone who you're not really related to. Hidden friend functions and friend operators, separate things, those are the greatest things since sliced bread. That's a different talk, though. I talked about inheritance. Oh, I went back an entire page. I was talking about matrix multiplications. If your class is a matrix and it has its certain size, it's compatible with certain other matrices when you want to multiply them together. And so you either multiply or add or scale or do some fancy 3D graphics with them. Really good for that, and it knows if it's compatible or not. And well, you can actually probably set it up to do a compiler error if it's in incompatible size. Yeah, constructors, destructors, build your class, get it initialized the way you want it, clean up after yourself. It's what you teach, we're talking about instructions for your kids. When your kid gets home from school and he makes himself a snack, and you get home and he's made the kitchen entire mess, I say he, yes, guys make more messes in the kitchen, that you should say, you're supposed to clean up after yourself. Don't you have any class? Oh, okay, I'm sorry. However, if you don't provide a lot of these operators, the compiler will infer what it thinks you want to do, and it will try and do the thing for you. 90% of the time, it does sometimes the right thing. The other 90%, it does the wrong thing. Yes, that's two 90s. So standard object-oriented, we got a class, it's a person. A person has a name and an age, and probably a bunch of other features. And you can test to see if they're equal to each other. Or actually, this is an assignment, which you really normally wouldn't assign a person, but a class you could. So this is protected from the outside. You can ask a class through a nice little friend operator function of, who are you? And it prints it out. It says, I'm Alex, and I'm 37, right? Close? No, okay, somewhere. Click. Okay, so we had imperative, declarative, functional, and procedural. Procedural is breaking down the program into all these different steps. Functional is a little bit of a special case because it's more of a mathematical basis, but those are really all kind of flavors of the same thing. Yeah, let's just call it just procedural. Okay, we got space in our list, we need more paradigms. We got object-oriented, we covered that already. Generic programming, of where you deal with your data in a generic way. This isn't necessarily templates yet. You can have a base class that is the implementation of a linked list that strings stuff together, and your derived class can implement the data holder, and you could be sorting numbers or names or records of some sort. That's a generic way of handling some of these data. Then we got templates. Templates came in a couple different styles over different eras of evolution. Initially, we just had templates of a vector or list or an array. Collections, we had simple manipulations on them. But then we started getting into meta programming. You got const expr and actually doing compile time stuff. So it's still all a lot of it's still all templates, but it's next generation templates. And I'll let you in a little backdoor, it's not a backdoor feature, and you've probably all used it. If you ever did a function and you didn't want to name the type of the parameter you were passing in, and you just said, we'll just call it an auto, and we're going to pass in a foo, even though you didn't put template bracket on it, that's a template. No matter what you pass in, it creates a separate function for every different type. And it tries to compile for each of those. And if some of the operations you do are invalid for that particular type, you'll get a compiler error. Same as you would if you did a template and you named what the types that you were trying to pass in, or you had a type name or class that you said you were passing in. That's a template. So with recent versions, templates have become a lot simpler to use. And that's for just a template function. You can't cheat and do that on a template class. You still have to name your types. Okay, so generic programming for a much wider style of data types without as much specialization. Generic algorithms, you could say sort the list that we had, but it wouldn't matter whether it was records or names or whatever. It would still know how to sort the order on them. The data and the methods for manipulating them are defined separately. You got your list of your data and your different sort algorithms or print algorithms, whatever. You treat them generically. Or other generic constructs. And that's what we talked about, the base class implements the list, the derived has the data. Templatization comes in a couple different flavors. We got the templates or template programming. That is also breaks down into either using a template or actually writing a template to do your own generic implementation of stuff. So you can use a template out of the standard template library of list or vector, and that's just consuming someone else's implementation. If you wanted to write your own template that does a foobar, and so you go off and you make a generic algorithm for doing this and you write your template for it, anything that your template can manipulate, you can try and at compile time pass in and say foobar int, foobar record, and if it knows how to do it, it will compile and you can manipulate it, whatever your algorithm was doing. So we have generative programming where that's where you're using a template, well, and actually both of them, that you say, I just want a vector of ints. It generates all the code you need for that. It's a much cleaner way of doing the macro copy, replace, or expand out with type safeness, and it generates all this code for you. And then we got the meta programming. Won't get too deep into a lot of that, but a lot of the stuff that we used to do at runtime for manipulating and testing data, you can get compile time, but you can also check, you can go pass stuff in and say, does this object have a plus operator? And so then you can decide if you're going to build your class, that it can add things using your template. And it can actually check to see if it doesn't have that and either not compile it or ignore it. If we're not going to have it, we're not going to try doing it. And I just kind of went through some of these examples. Applying templates to your code, writing your own templates, and the template meta programming, which is many times named TMP. It's not temporary, it's here to stay. So I had a red line before that talked about imperative, procedural, functional, and declarative, kind of a continuum this way. But we also have a paradigm in other angles. We had the POD, plain old data types, plain old data structures, object-oriented, and then our generic and our templates and our TMP that's really on a different axis. You can use any of the programming styles across the bottom in any of these. So all of the sample code that I was showing before, those were using standard template library, even when I was doing an imperative program. So you can mix and match. So and we'll get a little bit more into this, but it'll be kind of a punchline. C++ is not a multi-paradigm programming language. No one's going to argue? It's a multi-paradigm. or not multi, it's a mixed paradigm programming language. You can use any of these paradigms crossed and mixed inside of each other's. You can create templates that do things entirely imperatively or procedurally, or you can have procedural code that uses templates, and vice versa, mix them inside out. Some of the imperative programming with object-oriented, you've all seen this. This is when Visual Studio goes out and creates a wizard, also pronounced lizard, of its outline of a class, and then people between the curlies, they program it with C code. That's a mixed paradigm. And you can do imperative, object-oriented. It's ugly, it's stupid, it's not as clean as it can be. It's, as you evolve in your designs, you get better at it. So we have these, the original basis of the book definition, which is now kind of evolved into this book definition. And there's other definitions of it. I was saying a paradigm is a way of looking at data and how you manipulate it. You know, what about your whole system and all your algorithms about how do you manipulate stuff? There's other design pattern paradigms. Say you have a mainline program that just reads from the input, munches the data, and turns around and spits it out. You've all done this at a console, you know, ls-ls, pipe to more, pipe to sort, and then pipe it out, or an output to T and into a file. That's a process input output. So that is a paradigm of potentially how you would process data. This one happens to be somewhat functional, because in this case, I read all the strings, I convert them to upper, which is funny, STL does not have a to-upper function for string. You actually have to go through it character by character and convert each character uppercase to string. Long story of why they've done that, but it's it. So you actually, down below, we'd say to-upper, that takes a string. Here we do it in the function character by character. Super loop programming, when you're dealing on embedded devices. Yes, you have a main line, you never exit it. You do a setup and you say, while true forever, keep doing this loop. So your setup input, it sets up your input and output pins, and then you enter your loop and you do this over and over and over again. PWM, pulse width modification, you'd set what the level is. It's static, so it only initializes it the very first time through. We get what the input is, and then we set what the inverse of that out, the input is, and then that's just something to do to keep busy, to show you that it's working. And then we increase the pulse width modulation by 10 each time through the loop, so the LED will get brighter and brighter and brighter. And then once it gets up to a certain level, the maximum of 255, it mods it and it goes back to 0 and starts again and again and again. And then we sleep for 100 milliseconds. So you'll see it. It will run through about 25 loops, cycles of this, and bring it brighter and brighter, brighter. So about 2.5 seconds. That's the hello world for an embedded program, just to show that your device works. And that is a paradigm. That is how they look at the data. You set up your hardware, then you run the same thing over and over and over again. Not all embedded's that way, but that's one method of doing some embedded. State diagrams. If you have a system of how you're doing something, you go from one node to the next. That's the paradigm of how you look at the data. What's coming in? Where am I going to next? If you're playing tennis, that's a state diagram for tennis scoring. Starts off at love, love, 15 love, love 15. It goes all the way back and forth until you get over to either one side wins or the other side wins, or you get closer back to a tie. And I don't know all the fine rules of tennis. I used to play at a time, but we just hit the ball back and forth, and normally we go out before anything else happens. You get to deuce, you get add in, advantage, one person advantage the other person. And eventually, if you go back and forth enough, you're going to find your way to the edge. If you have a UART type device, some serial communication, it has a paradigm of how the device itself works, how you have to fill the buffer, when new data is coming in, what do you do with it? When do you trigger the device? The device also triggers interrupts back of that I have data ready to read. I have sent the data that's already out there. I need more data. And then you get the cases of where you get an error of input overflow. You gotta have to handle that all in your state. Then on top of that, the actual data you're sending has a state diagram of I'm sending this packet of data to this other guy and it's telling him, or quote unquote him, generic device, that I'm ready for another transaction, send it over to me. And it's, you know, they play ping pong back and forth sending data, and they have their handshaking protocols of how they do that. Just yet another state diagram on top of a state diagram, different layers of the OS. Simple state machine implemented with a switch statement that has an action or verb going into it. And depending on what state you're asking it to do, it says, well, is my current state compatible with that? I cannot start the switch if I haven't done anything, or if I'm already stopped, or if the command coming in is reset, there was something fatal that happened, I go through and reset the system. I can't tell it to stop unless I'm already started. So it's meaning that it's running. And if there's a default, if that's not what I wanted, it's an error. So this is, what state am I in? What state do I want to get to? Are they compatible with each other? If not, it's an error. And you set your current mode as that. This one is really hard to read. I actually stole this from a different talk. I call it a polymorphic state machine. And interpret this as a base class of each of these different state mechanisms. And you have a list of events and you're pumping them through the dispatcher. You say, do event, the dispatcher sends it off to the base. It only knows about the base. So it sends it there, and polymorphically, it figures out what type of object it is, state 1, state 2, or state 3. It goes through and it processes the event, it does a mod 3 on it, and if it passes that test, it sets what the next state will be. And one of the original examples of this is it actually news a new copy of what the next state will be and assigns that back as what the current state is. And then you delete the old state. So you really only have one state ever active at a time, but you always polymorphically ask it what its state is. And you ask, why would you ever want to do this? Say that you have some sort of plug-in interface for your application and someone else writes a plug-in module for it. They can drop it in, and the first thing it does is the initialize news of one of its states that this interface is in for this plugin, and it can go through and do all these different manipulations, whether do some graphics manipulations on your clip art or whatever it is you have, one of these paint programs, or do some sort of lens filtering to it. Your application has no idea what it really is, but you were able to call it this plugin and say, do this type of thing for me. That's why you might want to do it polymorphically as opposed to a switch yourself. This isn't a very clean example. Sorry about that. A Windows program. It's an event-driven state machine. A lot of people hate Windows SDK programming. It's basically just a big switch statement of what is the current event, how am I going to handle it, and you dispatch it off. If an event comes in when you're not expecting it, it would probably be an error. The way you start the message, the whole state machine, is you go through and you create a window, you load your accelerators, and you have a message pump, similar as on our previous slide where we had a message pump. This is translating the message and it dispatches it off. When we created this instance of this message, we pass it in a pointer to this WinProc. And so every event that comes along, the very first message is create. And you would go off and you set up a bunch of stuff for this particular window, what its interface was. In this case, we're just calling the default, or this is calling a WM create function that would go off and do stuff, set up your brushes, load any potential data needed for that window. It also has mechanisms for destroying it, painting the window. You wanted to paint in with the gradients of the colors, whatever for your background. The WM paint message handler would do that. It would get a paint DC, which would create you a DC you'd paint into, and you end DC. A command is, if someone pulls down the menu and they say edit, copy, the IDs would come there. And in this case, we only had two of them. We had an IDM exit, ID message for the exit or the about. For the about, we display an about dialog box. And the about itself puts up another window. It's its own SDK state machine, effectively. And when that exits, it comes back to this. And you just continue. If you don't know how to handle it, there's hundreds of functions. Most of them you don't have to handle. Many of them are internal. It's called diff window proc. It will handle it for you. If you don't need it, like pre-erase background, clipboard messages, before drawing the menus, the diff window proc will handle that for you, or you can overload it. So that's a switch statement, just like we had in the other one. Events come in and we switch on them. So it's a paradigm of how it processes and manipulates data. MFC, a lot of people really hate that for Windows programming. It is C++. And for its day, it was really, really good. It worked well. It was one of the big first application infrastructures for GUIs, and it worked pretty nicely. You have one document. You can look at this data in multiple ways. Say you had a spreadsheet data. It was a grid of data you were storing away in some sort of sparse matrix allocation. You could do a view of the grids of the data. Or you could plot that into a graph. It's the same data. It's just a different view of looking at it. A spreadsheet paradigm, which is different than the application paradigm, which is different from the programming paradigm that C++ uses. It worked pretty good. It was a doc view frame. So the application was part of the whole mechanism of the message routing for commands to the view, to the frame, and to the document. The document, even though it's just a object without a window, you could actually route messages to it and handle menu commands in a document. So it had its paradigm of how it routes messages through the system, and the application would then process them. That was its paradigm. Different paradigm than we're talking about. MVC, it's model view controller. C# likes using this, some Java stuff. I don't really know them super well. Sometimes they're modeled in a Y shape, sometimes in a triangular shape, where each of these have a relationship to each other. It's the same type of thing as MFC of the doc view frame. Sometimes, but a lot of times in like a C#, you're not dealing with an actual frame. It's a server that you're talking to where you're getting your data and sending commands. I'm not going to embarrass myself because I don't know it real well. But it is a way of dealing with data and controlling it. Qt can do an MVC type of interface also, but Qt also has a different type of paradigm that it uses. It has its own flavor of event routing. You can take a particular event. Here, in this case, all we do is creating an application object. This is an object, it's an application. When it's created, it connects this tray icon that it created, which is an icon that's going to sit down in your tray. And when it's activated, it's going to call this class with this function. So it sits there and it sits there. Someone clicks on it, icon's activated, it calls this function. And it throws up a message box saying notification. That is a paradigm of how Qt pairs and routes commands. Is it a programming language paradigm that C++ is defined in C++? No, it's its paradigm of how it processes things. the office clerk stamping things and how it connects them and staples the forms together. That's just how it knows to work. That's how you have to work with it. At its paradigm, not one of our paradigms. Different data models. If you have some sort of database, you manage records, you can manage, look at these and lay them out in design and conceptual or logical or physical, different layers of what do we we're gonna store records of customers. Logical, we're gonna break these down into different pieces. Physical, this is how the size we're gonna put in the database and what the relationships are gonna be. The abstract representation or high level, and sometimes entity relationships of how do two different entities in a database connect. The user buys a product, they put it in their cart, then they buy it, and yada yada. So it's just how the relationships you can have between these different things. And people, this is a different entity relationship. This is a students and faculty and classes that are built up in what they're made of and what their relationships are to each other. The actual logic of them doesn't matter, just you say there are relationships. Students don't directly have connections to a lecturer. They may have, they're not gonna necessarily have the same name unless it's someone's daughter sitting in on their class. They may have the same name, but they're still separate people. A different student and lecturer. And a student to take that class has to have an enrollment. They have to be enrolled in that school or enrolled in that class. This is just how they're related to each other. That's a paradigm of how they look at that data. Logical models is, you're back to our customer product order. What is a customer made of? What is a product made of? What are the relationships between them? Your customer can have 0 or more orders in their cart. So an order corresponds to at least one product. You can't have an order where you're not going to buy anything. Doesn't make any sense to go through a checkout of that. And constraints, this is kind of things that rules of how the database would be laid out for this set of entity relationships. And so it's a pseudo CRM system, but this is an actual physical model, the database declaration, saying the product ID, in this database, it's a primary key, it's an integer. The product name is a character that's limited to 100 characters, because that's how big it is. The description and what the price is. And you say it has 2 decimal places in it because we're dealing in dollars and cents. And it's just very exactly how it's laid out. Very specific, if you know what it is you're looking at, it's very informative to you for your design. And then you have the indexes, which we kind of talked about, primary key and whatnot, of you can look up any customer by their primary key or any product, and then you have relationships of keys in the order table. If you're doing it with AIs, LLMs, I do not know what mechanism they use internally, and they constantly keep changing because the design itself is evolving. AI is not evolving, they're not taking over and thinking for themselves. That's us changing what their models are. But it has a database where it stores this stuff away. It has its knowledge graph of how these different entities relate to each other, and you give it the training, and then you can feed it a question, and it's able to take from all of its training and deduce things. Inside of the orange square there, it knows how to figure out this data. It has a data model inside of that, its paradigm. It's not a programming language paradigm, it's its paradigm of how it works. If your application around it may have a data paradigm of how it passes data into it, it might be in a stateless or stateful web interface. You fire up ChatGPT, it remembers from one question to the next the context of what you've done. It's a stateful interface. It has a paradigm of how that interface works and how it calls the backend API. And it looks up the state stuff based on what you've previously talked about when it gives an answer and says, well, it's either yellow or red. And you say, no, it's not red. Then it comes back with the answer, okay, it's yellow. It can deduce these things and build up memory. It has a paradigm of how these interfaces work. So this is the Wikipedia version of the definition of a multi-paradigm programming. And then they go off and they list a whole bunch of others. There's also concurrent, which goes beyond. We had our two-dimensional graph. Go back, or go to where you're supposed to be, that it goes in. Once you start throwing in threads in there, we needed to add another axis on that, because each of your different modules and threads can be using multiple different paradigms and programmed differently, but these programming, the threads have to be able to interface with each other. That's their paradigm of how they have to work and synchronize control between them. That's the concurrent programming model. And you can have whatever model it is you want where you have good synchronization between each other. Constraints, you set up relationships, like that database example, where it can do certain types of relationships or can't. You can do other things with it too. Say a spreadsheet can be built off of constraints, and it tries to do some sort of solving algorithm. There's a whole list of different stuff. We got our declarative distributed. It's like multi-threaded, but you want to send it off to another computer or store it off in some other receptacle someplace. Logic programming could actually be dealing with mathematical logics of sets that you're dealing with. If you're doing the union of sets, intersections, sorting sets, or the logic could be actually electrical logic of this wire and this wire, AND gates and OR gates and XORs, and you could have it do its computing. And for programming in FPGA, there's actually a programming language where you set out the mathematics of what you want the circuit to do, compile it, and it will program that into your FPGA device. So it'll work in nanoseconds rather than actually having to go through all the steps of the logic. Very, very handy, especially if you're dealing with low-level embedded and you need super fast if you're doing a SATA controller, which I did on one project. I interfaced with an FPGA where it would give us megabytes of data that it would blast through this connection super fast. We get down to some metaprogramming. You got template, reflective. We don't have that in C++ yet. Coming. But it's some metaprogramming on using reflection. And so there's a whole different slew of different styles of programming. The pipeline we talked about, that's like the input, process, output. There's also a style of programming where if you do something to a particular collection, then you can do dot and take a subset of that or do a transaction or a transform on that, and the results of that, then you do something else to and something else to. And I haven't really gotten into any of this, but there's some styles of programming that rather than doing continual dots of sets, they actually use a Zephyr stroke or a pipe symbol as an operator, and they output one stage into the next stage, into the next stage, using many different database programming techniques. They're using for filters and views, for looking at subsets of data, where you're breaking up your data into different modular stuff. There's some examples out on the web I need to get into better. This is part of the Wikipedia graph of different programming languages and different paradigms they have. C++ is one of the more multi-paradigm, mixed paradigms that you can use. Some languages, when they have multi-paradigm, you got to use this paradigm or this paradigm or this paradigm. You got a lot of different options out there. C++ is one of the more flexible, better ones. It's got either partially or fully implemented most of the way across. whereas the others tend not to. There's this blow up of C++ of that line. How many paradigms does it say that it has? And there are concurrent and functional, but we kind of, concurrent I talked about with threading. Constraints, there's a lot of outside libraries you can use to drag in that if there's a particular constraint or paradigm that you don't have, somebody else has probably written something to do it. It's not necessarily a programming paradigm, it's a data manipulation paradigm. So got to be careful when you say paradigm. When you're dealing with religions, there's something called tradition. And there's a big T of say, this is the way canon law says this particular rite has to be done. And there's the little t of, well, we've always done it this way. So that's the same way with us. We have big P of paradigm and little p of paradigm. It has to be this way or it can be done this way. So paradigms is a difference in languages imposed by the compiler itself. We're not supposed to, you shouldn't confuse paradigms with paradigms. And many paradigms are actually styles of programming of how you use it. Data model programs or how you manage and manipulate your data, frameworks or application paradigms can be big P, can be little p, depending on how you've used them and which type, like the example of Qt I was giving. So as I started with, a paradigm is it's a perspective. It's how you're looking at it. So it's not only how you're looking at it, but how you look at, how your paradigm is that you look at, so of what it really means. So C++ is a mixed paradigm programming language. It's more than is a multi. You can mix all of your different paradigms. Yeah, sometimes it's easiest to do one just a simple way, and inside of an object, sometimes you want it complex. Inside a template, it can be simpler, complex. Paradigms have limits of what they can do. Your mind doesn't. So expand your mind, think in new ways, break your models, your preconceived conception, which is why you're here to learn. Questions?